Okay, in this demo, I'm going to show our latest feature coming in the latest release of Coreform Cubit, which is the ability to connect to your favorite large language model, AI agent to work with Cubit. So I'm going to show you this within VS Code, and you can follow along from here. I'm specifically going to also use Claude for this work. To begin, I'm going to get myself a terminal. So I'm going to go to the file menu here. Actually, first I'm going to start a timer here so you can watch how long this takes. I'm going to start a new terminal. And then what we do is we'll want to run, we'll want to run or launch Coreform Cubit with our RPC argument. So C program files, Coreform Cubit 26.8, Coreform Cubit.batch -RPC. That will bring up an instance of Coreform Cubit that's now connected. Put this off to the side here. Now I can open up my Claude session, and I'll create a new session here. And I'll start by telling Claude that I want it to please use, there's a cubitc item in our interface. Please use Python 3 to drive the Cubit GUI session that I've just started in my VS Code terminal with command . And then I'm going to go ahead and give myself, I'm going to switch my model here. I'll use Fable, have auto permission. Okay. And I'll ask it to go. So Claude is now connecting to my session. You can see here now that Claude has started issuing some commands here, so it's able to connect. All right, this is great. So now it's asking me what I'd like for it to do. And what I'd like to do for you today is to dive into challenges with web cutting and partitioning of CAD geometry for meshing, and maybe to try to get some insight into that. So what I'm going to do is I'm going to point it to that there is a file in our installation of Coreform Cubit. If we search for the knuckle, let's copy the path location. Okay. I'm going to ask it, can you import this CAD geometry? And that is the knuckle.sat. Great, and you can see it has gone ahead and has imported that knuckle geometry. That's fantastic. Now, what I've previously done is I have created a journal file. What I want to see is that as we do things like partition our CAD geometry, so let's say that we do a plane from curve. If I cut my geometry here near this vertex, all right, this would be the cut that I would do. There is a single volume, but if I cut it, I now have 3 volumes. And these 3 volumes, if I draw this, there are surfaces that are at those intersections. If I draw the other 2 volumes, say, they have their own. And what I want to do is I want to interrogate the topology, the graph structure of this geometry as I do web cuts. So I've specifically have previously created a journal file. And what I'm going to ask it to do is I want to create a graph after each of these operations that I can then visualize. So what I'm going to do is I'm going to say this. I'm going to copy this, this content. I'm going to say I would like to explore the effect of web cutting, imprinting, and merging operations on the BREP topology of this knuckle geometry. Specifically, I would like to create a series of graph plots showing the BREP topology at a series of steps. The journal file I would like to run is, I'll give it, this has a code block where you will create PNG images at each of the, I'll copy this little, make the graph image here, comments. This should probably, I would like to run this. Oh, let's not even ask that. Let's see if it has any. Can you help me design this capability? Using built-in Coreform Cubit Python API to query topology. Okay, and we'll ask that question. So it's going off and trying to grab to see what's available. I may or may not have Network X or any of these on this system. I don't recall for certain. You can see here that now Claude is grabbing information about the different methods that are available. Okay, so now Claude has finished its work and it's built some tools for me. Let's go ahead and take a look at these. So here's the directory that it built. Here is a Python script. So you can see it's created the functions for me to be able to get the information about the topology. It's created the journal file of the knuckle and copied that from what I had given it. And then it's created the outputs. So let's look at outputs here. And we can look at the different PNG files. So this is one of the things I want to bring up and mention then. So let's go ahead and take a look at all of these different aspects. So if we have our journal file, if we start on this first step of let's import the CAD geometry, you can see that what we have is we have a single volume. This matches that then has 23 surfaces. And we can see that then all of those surfaces are attached to that one volume. And then the connectivity of each of those surfaces to their bounding curves, and then each curve to its vertex. And again, none of these entities here are unused or duplicated. If we look at the next step, so this is where we did that web cut. So let's apply this web cut. Now we have 3 volumes. And what I want to point out is that we have these sharp, disconnected entities now. You can see that volume 2 doesn't have any surfaces that it shares with volume 1. And same for volume 3. Does not share any of those surfaces or curves. Now Cubit, when we mesh, we begin by meshing the vertices, and that's kind of trivial. The vertices are already meshed, but we then mesh all of the bounding curves, and then we mesh the surfaces of those curves, and then we mesh the volumes. And the mesh on surface 3 does not affect the mesh on any of the other volume surfaces because there's no connectivity there. And so as we continue along with our web cutting, so we do another web cut to cut off this shoulder here. We have a new volume. And again, there are these distinct separations between the individual volumes, new surface IDs, since new surfaces aren't created. We chop off the other shoulder. That same process occurs. And then we cut through. We extended this surface to cut out this cylindrical region. And then we cut this volume. We separated it from its base by extending the surface on top of this volume. Again, separate, distinct entities. And now we start getting an even more complex graph. So that was, I cut this in half, and I cut it in half the other way. So you can see, especially as I start now doing a lot of these cuts, right? We can see this in our model tree that I have a lot of entities, 20 volumes. It starts to now get kind of difficult to see all these different volumes. We do another cut that cut off these edges. And again, another cut. And then now what we do is we will composite. We have these complex surfaces. So this is a challenge that if I were to try to mesh this volume, just look at it by itself. I could define a many to one sweep. I could say, let me mesh this volume by detecting that I have these entities, and that's again volume 14. Let's even see if we can look at or find volume 14 in here. So here's volume 14, and it has these surfaces. What Cubit tries to do is it tries to identify, can I take these surfaces and can I determine what maybe links them from top to bottom in a sweep direction? And that's the problem that Cubit is trying to solve. And it can do things like maybe look at some idea about the geometry. But if we ourselves can determine that this is the sweep direction, Cubit can then say, well, from those surface IDs to this surface, what are the edges, what are the curves that connect these two top surfaces to this bottom surface? And if it can do that, then it will build this mesh. But the challenge here is that because we mesh those curves first, we have to respect the vertices, this quad element that then is swept will then turn into what we call a kite-shaped element. And that's a poor quality element. So instead what we might want to do is I can modify my topology to ignore this curve by compositing the surfaces together. So if I do that composite, you can see that now that curve is now a light, let me change here off selection mode, is a light green curve. Which means that Cubit will ignore it. If my mesh is fine enough, so if I choose a very small mesh, any nodes that fall inside of that region will still be exactly on that surface that we ignored. But the key is that it now no longer has to respect that curve that had existed there. So you can see that no longer respects it. Now these are still not a great element, maybe quality here. So this is where maybe I want to specify a different scheme. Like maybe I'd want to specify a polyhedron scheme. And again, if Cubit can understand the topology, then and how that fits with its polyhedron scheme, then it can build a polyhedron mesh. But the challenge here, if I refresh my display, is that again, because none of these volumes share any kind of connectivity, if I were to say mesh vol all, well, the mesh here just happens to be really close, but I could actually do this. Let's go this. We could set a very coarse mesh here. And I can mesh all the volumes. You can see that there's clearly not any connectivity between these different entities. And in fact, you can even see that here as well. These are all disconnected. They have no knowledge about their neighboring volumes because they don't share any of that knowledge. Now, if we merge suddenly now, if we do this merge vol all, if we look at our graph structure here, now I have shared volumes or merged volumes. And so now you can see that volume 2 does have, or I should say volume 4 shares surface 106 with volume 1. So what ends up happening is that Cubit, as it's building its mesh, it'll start by meshing vertices and meshing the curves. And if those curves are shared by a surface, then that surface gets those two surfaces that share the curves will have the same mesh on their curves. And that surface is meshed. And because that surface is shared by both volumes or multiple volumes, I guess it'll only be 2 volumes here, that's what then enforces that the mesh between 1 in volume 4 is coincident or merged or C0 continuous at that surface boundary. And that's the workflow that Cubit does. And the great challenge in meshing in general is to say, when I have this complex graph structure, how can I build or generate a mesh? How do I propagate mesh sizes across all of these curves and all of these surfaces out to their volumes? And that's the mathematics problem that is solved by Coreform Cubit. So now if we mesh all, you can see that, oops, I forgot to merge the volumes. And you can see that this is where Cubit has struggled to build the mesh on that volume. If instead I come through and define, I know that these volumes need a polyhedron mesh, I can help Cubit solve that mathematics problem. And now if I ask Cubit mesh all, it's now created that mesh for me. And that is why we sometimes in Coreform Cubit, we call it a semi-automatic meshing tool, because if it can recognize how to take a topology and build a mesh, then it can. If it can't, we sometimes have to give it guidance, like telling it what scheme to use on certain volumes for it to then be able to solve the rest of that problem. So hopefully this was an interesting demonstration of how not only how Coreform Cubit's imprint and merge and meshing routines work, but also in how we were able to use Cubit's new RPC method to communicate with LLMs to solve complex problems.